Guys, welcome back. We're going to try an outside video for this one. I'm trying to get tired of being cooped up in my house. I'm sure you guys are too. So we're going to be out here with the dogs. Hopefully they won't be too distracting if they walk behind me or they start barking at something. But I did want to come back in and talk a little bit more about the problem that we were finishing up last time because kind of my 15 minutes was up, so we kind of ended pretty quickly. But I do want to talk about this, when is f of x changing the fastest again? And so the idea was is that you had to realize that you were doing an optimization problem. And so we were working on an EBT argument. Now, do realize that an EBT argument is not the only thing that we could have done for this problem. Um, I did it by looking at g of x being continuous on 0 to 14. Therefore, I could use EBT and just kind of went through and took the derivative and so on. But you could also have done this problem by using the fact that on the interval from 0 to 14, there's only one critical point. So the alternative to that, I'll just put that in red down here kind of as I'm looking at it, that you could have also said the f of x changes the fastest at t equal to 10 or 4 p.m. because on 0 to 14, the value x equal to 10 is the only critical point, and our function f of x is going to increase from 0 to 10 because f prime of x, which was equal to g of x, was positive, greater than 0 for 0 to 10, and f of x decreases 10 to 14. Oops, it'd be helpful. I'll make sure that you guys can see that. Decreases 10 to 14 because f prime of x, which was equal to g of x, was less than 0 for 10 to 14. Let's probably change that to a parentheses as we're looking at there. All right, so that kind of gives you two options on that. So just kind of reminding you, the red that I put in here is going to be option number 2. We don't need both of them. You can either do an EBT argument, or you can do the, there's only one critical value on the interval, and the function is only doing this. And I guess technically, like the third option on that, while we're sitting here talking about different options for optimization, you could have also, once you got your critical value, went to your second derivative, and your second derivative is -2, which is less than 0 for all x. So we could have also said it's the only critical point, and it's the only critical point where you have a second derivative that is negative for the entire interval. Therefore, it would also be a relative maximum, which becomes a absolute max because it's only one critical point. So I just thought I would highlight that a little bit more in this part 2 of this video about the fundamental theorem of calculus. All right, so let's kind of finalize kind of what the main points are of taking a look about this. And there are many parts to the fundamental theorem of calculus. This is just the first part of kind of understand what's going on with it. So the first thing is this idea that we have an accumulation function. And that accumulation function, which we've kind of been working with all along, outputs the net area. Okay, and I'm going to stress that idea that it is net area, because remember that we're adding positive accumulation if the rate function is above, and being negative accumulation taking away if the rate function is below. So we have this accumulation function, and it outputs the net area under the rate function curve, whatever is representing the rate function, from a starting value, a set starting value, to x, which is going to be our input to the function. So kind of as we're taking a look at this, The idea is, and I'm going to start using a little bit, instead of using the g and the f of x that we were using in the previous example, we're going to say that our net area function is going to go from a starting value c, all right? So I'm going to come over here. I'm just going to call it c. So it can be more generic. We started at 0 in our problem, but it can start anywhere at once. This could be our accumulation from 5 hours after we started, or it could be the accumulation 15 hours after we started. So there's a certain starting value that's a constant that you will know. We're going to plug that in to x, which is going to be our upper bound, and that's the variable in this problem is the upper bound. And usually when we're looking at the derivative function, remember, I don't always have to call it f prime. We called it g in the last one. So in this one, I'm going to call it lowercase f. And then remember that the variable of integration is going to be a placeholder for this. So you have to use a different letter than what we're using for the x. Don't do c to x, f of x dx. This has to be a different variable. Think of it like you have two children. We already named the first child x, and that's going to be our input up here. You can't name another variable to stand for the same thing, so we want to make sure that that is kind of a different letter. And if I'm using lowercase f inside of the function to represent the derivative, remember that we will always use capital F to represent the antiderivative, or one of the antiderivatives of that. And this capital F is going to be a function of x, because it's going to match our input, which is the upper bound. And we're going to remember that this function is a net accumulation function from c to x. And so that's what's called our accumulation function that we're talking about. The second part, there's another part of FTC that's going to talk about the relationship of this net accumulation function to actual antiderivatives, but we'll come in with that a little bit later. So let's just remind you that this is your independent variable right here. This one is going to be your placeholder variable. Right. This function in here is your rate function. And then out here, of course, is your net accumulation function that we're taking a look at. Right. And so the idea is that we're going to recall, I'm just going to put it over here on the side, that this little f of t is actually the derivative of the function that is on the outside. Now, notation-wise, and I just started to do that incorrectly, that derivative, if I'm taking the derivative of capital F of x, then it's got to be in terms of x. So the function on the inside, the rate function, even though it has this placeholder variable, if I'm talking about it as the derivative of the accumulation function, then we have to make sure that we switch the placeholder variable back to x to represent our input, which is that upper bound. All right, and so this is actually what part 1 of the fundamental theorem is. So part 1 of FTC is that if I am going to have this accumulation function, capital F of x, and with this accumulation function, I want to take the derivative with respect to x of this accumulation function, f of x, that what we're doing is taking the derivative with respect to x of the definite integral from c to x of f of t dt. And we will remind ourselves that the variable here is the variable that we are taking the derivative with respect to. I may want to include parentheses around this whole definite integral that we have in there. And that when you take the derivative of the definite integral, the derivative is the rate function that is inside of the definite integral. And the only difference is that now it is going to be a function of x. And like I said, we'll talk more about this as we go through. All right, so that kind of finishes up the part 1 of FTC. And so what I would like you to do is to go ahead and work on the check your understanding here. And I will put up a separate video and the key to this so that we can kind of highlight some of the things that are important in this practice problems that you have. Work a little bit on your notation, because I know that's something that the AP is fairly strict on. So use good notation. Don't do sloppiness when you're doing this check your understanding. and we'll come back in and we'll discuss that in the next video.